So good morning, everyone. I hope you can hear me loud and clear and that you can see my writing. Today might be the last lecture, but if not, there'll not be much to go. We'll finish the stuff on Wednesday. So as usual, the plan for today starts with a recap of what we did last time. It's quantization noise. We established that VQ, the RMS value, is given by VLSB divided by root 12. And of course, we know that VLSB is equal to VREF over 2 to power n. And this is independent of Fs, or the sampling period. Just as a reminder, we used a description of noise power. The power is directly proportional to voltage square, so it's VQ RMS squared, and this would be VLSB squared over 12. So the noise power arising from quantization is given by that expression, or if we get it in terms of voltage, it's given by that expression. And we can only reduce it if we increase the number of bits we use to digitize our sample. So that's the first thing we did. And then we defined what we call the signal to noise ratio. And the signal to noise ratio is signal divided by VQ. And for the signal, we used a sinusoid whose value is VREF, amplitude is VREF divided by 2. And if we get the RMS value of that, the signal is equal to that. And therefore, the signal to noise ratio, we work that out. I'll just get the value from my handout. But that worked out to 2 to power n root 1.5. And if we write the signal to noise ratio in decibels, this becomes 6.02 n plus 1.76 dB. So we can write it as a normal expression, or we can write it as in decibels. We take 20 log this value, and you end up with that. So the signal to noise ratio is a figure of merit we can use for analog to digital converters to see how good the converter is. The bigger the value, that means your noise level is lower compared to the signal level, and that would be a better ADC. Then we looked at oversampling, where your sampling frequency K is equal to, and Fs is Nyquist frequency sampling, Nyquist rate sampling, and K is much greater than 1. K, I don't think we gave this a name. It's also called oversampling ratio. If you check textbooks, that would be called the oversampling ratio. By how many times are you sampling beyond what you need to recover the signal? For this particular case, because the quantization noise is independent of sampling, VQ RMS is in the exactly the same as in the case for and a sampling rate. So as the case for Nyquist rate, so it's equal to that. And noise power, which we can call PQ, is equal to VQ squared. This is the RMS value, and this will be VLSB over squared over 12. The difference between this scenario where we are sampling at FS, and this scenario where we are sampling at a much higher rate, I'll summarize that because that's important using the two cartoons. So this is FS, this is FS prime, and if I do VQ squared, understand this to be RMS, this is noise power, and that's FS, then the noise would be something like that. If we are on the same scale, and this is FS prime, and this is VQ squared RMS, then the noise will be that, but it's spread over a much wider frequency band. So the noise power across this band is the same as the noise power there. So the noise power spectral density here is reduced. So we can say noise power per unit frequencies. So when we say spectral density can be confusing, but it's essentially the noise power per unit frequency or noise power spectral density is reduced. But we know that our signal exists, our baseband signal. If we are to compare this with the Nyquist rate, we can have a filter that eventually only allows this to pass through, and therefore the effective noise here is reduced. Yeah, so what we need to find out, what is the signal to noise ratio here? Yeah, but we can expect the signal to noise ratio to be bigger because the quantization noise in the pass band is reduced. So we'll do that over the next 5 minutes. So for the second case, where we are oversampling, noise power PQ is equal to VQ squared RMS, and this is VLSB squared over 12. So it's identical to the noise power for this earlier case. We can say noise power per unit frequency, which is the power spectral density. This will be equal to PQ divided by KFS. So the noise power divided by the frequency range over which the noise exists. So we make the assumption that the noise is uniform, or it's also the expression white noise is used, that the noise is spread uniformly across this frequency range. And this means that noise power over Fs, which is the equivalent Nyquist band, that noise power would be equal to PQ over K. So I can say PQ prime, that would be, so over just Fs, the noise power will be the noise power density times the band over which that exists, which is Fs, which is a Nyquist rate. So the noise power would be equal to that. And therefore, the quantization noise, this one we can write it as VLSB squared over 12K, because PQ is given by that. If we put it in, we get that. And therefore, the equivalent noise, the RMS value, will be just the square root of this, which is VLSB over root 12K. Usually, because this are digital systems, we choose K to be a factor of 2, so 2 to power m. And therefore, we can write this in terms of m. So the signal to noise ratio is equal to the signal divided by VQ. In this particular case, this is the noise voltage signal of the oversampled signal, but only considering the noise level, which is in the band of interest, so which is only over the frequency 0 to Fs. The signal, we know it's Vref divided by 2 root 2, and this will be divided by that, and this will be root 12K over VLSB. VLSB is Vref divided by 2 to power n, so I can write this as 2 to power n there. Now I think this becomes multiplication. That comes to the bottom and that goes to the top. The two VREFs cancel, and here we'll have 2 to power n. If we put k into this expression, we'll have 2 to power 0.5 m from this k, and then we'll have root 12 to root 2. And if we simplify this, this will be 2 to n plus 0.5. I think it simplifies to 1.5. So this on the top it becomes root 6. If you put the 2 inside, it becomes 4. That comes to 1.5, and I think we have an m there. So the signal to noise ratio becomes this, and that's almost identical to the signal to noise ratio for the Nyquist case. If I just show that for a minute, for the Nyquist rate ADCs, the signal to noise ratio is equal to that. If we take that in decibels, if we take 20 log this value, we get this. And similarly, if we write the signal to noise ratio in decibels, this will be 6.02 n plus 0.5 m plus 1.76 decibels. We know that n represents the number of bits, and therefore this expression tells us that, and we have n plus a quantity which is 0.5 m. So this 0.5 m essentially represents an improvement in the signal to noise ratio. If we choose m to be equal to 2, it corresponds to adding an extra bit to our ADC. If we choose m is equal to 4, it corresponds to adding 2 bits to our ADC, because the effective number of bits. So we define n plus 0.5 m as effective number of bits We know n corresponds to the actual number of bits in an ADC. But from this mathematical consideration, we have an effective, the effective number of n can go up by our choice of m. So if we choose m to be large, we essentially increase the effective number of bits. That's what the math tells us, but eventually, actually, when you design an ADC this way and you do oversampling, you end up with the higher resolution or a higher effective number of bits. So with m is equal to 1, we have an additional 1 bit. No, with m is equal to 2. So if we oversample by a factor of 2, we have an additional bit. With m is equal to 4, we have an additional 2 bits. And so if we wanted, so often we can choose n to be equal to 1. So we simplify our basic Nyquist rate ADC and m to be large to achieve, for instance, 16-bit resolution. But we really don't do it in this architecture. So any questions before I carry on? I'll just draw or show the architecture of an ADC. This is figure 62 in your handout. We have an anti-aliasing filter. We discussed this a little bit in the revision class on Wednesday. We oversample with an oversampling ratio of k. Actually, when we oversample, this is redundant. We really don't need that, but we show it here for completeness. And when we oversample, we create extra bits through the oversampling process. And once we've done that, we can just consider the signal that's within our bandwidth of interest, so up to fs. So we use fs. This is for just mathematical analysis to get figure of merit. So we know our actual signal exists up to fs/2, but we can use up to fs for this. So any questions or comments before we carry on? So the math tells us that the signal to noise ratio for an oversampled oversampling ADC is 2 to n plus 0.5 m times root 1.5. So that factor is, we know n is the number of bits. So by oversampling, what the math tells us is that we can generate new bits, and how many it gives, that expression gives us for actual numbers. So if you do it in decibels, you also get the same thing. So the third thing we look at is feedback in ADCs. Actual oversampling on its own is not used, and we'll discuss that, I think, at the revision class on Wednesday. But we'll just do the theory today. But introducing feedback, we can reduce VQ even further. So we've seen that by oversampling, we spread the noise over a larger frequency band, and in the band of interest, the noise level is reduced. So effectively, our signal to noise ratio becomes bigger. We can make that even bigger by introducing feedback in the system. So before we actually do that for an ADC, just some basic information about feedback. So in feedback systems, you'd have an input signal, which we can call V in. And because we have feedback, we can have the feedback signal can either be negatively, it can be subtracted from the input. We call that to be negative feedback, or it can be positively added to the system. We call that to be positive feedback. Many of you will know this from your earlier classes. If we consider an amplifier, for example, of gain A, and it has, so it amplifies the input signal. And let's assume that this amplifier introduces a noise signal Vn. So through the amplification process, there's a noise that is introduced. And as we'll see shortly when we look at the feedback ADCs, this corresponds quite, and that's our output signal. Then we can have, this is the feedback path, and we can scale the output signal by a factor beta. Once we've scaled it back, we subtract it from the input. And if we do this, we call this negative feedback. And you do this in amplifier design. You also, negative feedback, you do this in amplifier design. In oscillator design, you normally use positive feedback. But in amplifiers, in stable systems, you'll employ negative feedback. Those of you doing control systems, this will be very familiar concepts. Yeah, so if this is the output signal V out, so the signal here will be beta times V out. We scale it by a value beta, and the signal at that point will be V in minus beta times V out. And therefore the signal at this point, Vx will be, it's an amplifier, so we have A into V in minus beta times V out. And that will be the signal here. It's the input signal just amplified by factor A. And finally, we can write that V out is equal to Vx plus Vn, or I can call this noise just to be clear. So if the amplification process introduces noise, I can show it explicitly like that. That we have an effective added noise there, and this will be A V in beta V out plus V noise. If you don't follow how that expression has come out, V out is equal to that expression, please do ask, and it comes from this. Those of you who've done control system is pretty straightforward. So without the feedback, without that path there, in a normal amplifier, you have your input signal, it goes to the amplifier, we get the output. And if the amplifier introduces noise, that noise is also the output. What we've done, I've probably drawn something like that. So a normal amplifier system, V in gets amplified, it goes to the output, and a noise component may be added to it. What we want to see is what happens if we take some of the output and feed it back to the input. As it turns out, we'll see that it can help us to reduce this added noise component. So out of, once we introduce feedback, the relationship between the output voltage and the input voltage is this. Yeah, but some of the output voltage is fed back to the input, so it's equal to that. So I'll write out that expression again. So I have V out. V out is equal to A into V in minus beta times V out plus V noise. So from that feedback diagram, we get that expression. We can make V out the subject of this equation. So I can say V out into 1. If we take this term to the left-hand side, this would be beta times A. And this would be A V in plus V noise. And so if we make V out the subject, we have A V in 1 plus beta times A plus V noise divided by 1 plus beta times A. So beta is a constant, it's a factor, and we can, for this simplistic analysis, I shall choose beta to be equal to 1. And actually in an ADC with a feedback, beta is actually equal to 1. So that assumption is not too far off the mark. And if I choose A to be much greater than 1, so I make some engineering choices. I can call them engineering choices. So these are considered choices. Beta is equal to 1, and A is much greater than 1. That means that this component becomes quite small. And if A is much greater than 1, then this ratio is also very close to 1. And therefore, V out is very close to V in. And or V out reproduces V in. So in the processing of the signal, we don't want to lose information. So when V out is as close as possible to V in, that's good for us. Okay, for analog signals in an amplifier, this might not make sense because it's equal to that. But in ADCs, V out is actually a digital signal. V in is an analog signal. And we want them, the two signals to really have the same value. So what feedback does, if we choose our gain to be high enough, the added noise onto our system, its impact on the output signal is very much reduced. Questions or comments? So if there are questions, comments, we'll see how feedback is used in ADCs. So our typical ADC, do you have any control besides amplification? And I think let's just do the ADC with feedback, and then we can come back to the question if it's still valid now. So ADC without feedback. First of all, we just, so we have our V in. It probably goes into an aliasing filter. It goes into our ADC. We have so ADC without feedback will be equal to that. If we want to introduce feedback, without feedback, it looks like that. So if we want to introduce feedback, so I'll do ADC with feedback. So I'll still have my V in. I can go to my anti-aliasing filter. After this, I can go to ADC. And here I go to B out. But this output signal, I'd like to feed it back to the input so that any noise that is introduced due to the analog digital conversion process, and we know quantization noise is introduced. So I can put that into a DSC. I have an analog input, and this one, I'll need to add it to the input signal. So how should we do that so that the inputs, the system still works for us? So if we want to introduce feedback, we just take our digital output, use a DSC, convert it into an input signal, and then I leave this as a question mark, and that question mark will resolve it as follows. So we'll do an illustration of what happens within an ADC. So if that's time 0, the first sample, the second sample, and the third sample, and so on and so forth. So the first sample, we get the amplitude of the signal. We digitize it. For the second sample, we take the amplitude of the signal, but we fed back the first sample. So if it's not much. So when we do the second sample, the amplitude of the second sample in this particular sketch is lower than the first sample, but what is fed back is what was the previous sample. So at this point, we have a difference between those two. So to do, if this is my V in, the signal which is fed back is so if my first sample is at time t is equal to 0, this goes through the system here, it gets digitized, and that's fed back here. So the signal that's coming back here corresponds to time t is equal to 0. The signal that we've just sampled corresponds to time t. So the signal that comes here will be the difference between the current sample and the previous sample. We call it delta, or that's the different signal between the current sample and the previous sample. And then here we come into what I can call a black box. And this black box should still remember the old signal at time t is equal to 0, and it should add on this delta, and in this particular case the delta is negative, so it subtracts from the original signal. So at this point we have this signal at so I can put that as a question mark. We have the signal that corresponds to the sample at time t. And so once we have that correct signal there, we go through an ADC, and the ADC gives us B out there, and this B out, we come into a DSC, and the DSC feeds back there. So when we go to time 2t, so the input signal is the new sample there. That's not quite a good step. It's a new sample there. So at time 2t, the signal which is being fed back is the previous one, which is at time t. That's what's coming in there. So the difference between those two appears here. We have the old sample in this unit, and this unit adds the difference, and we create the new amplitude there. And once we create the new amplitude corresponding to this, we go to ADC, we digitize, and we do that. So probably this sketch wasn't, I'll just use a sketch where this varies a little bit more. So if that is 0, that's the first sample, T, twice T. So the difference between, the first sample comes in, this nothing fed back is 0. So here, the first sample will be here. It comes into this unit. This unit is the first time it's doing the ADC. So the whole signal appears at the output here and is digitized. Once it's digitized, we have the output, but we feed back the value that we have back to the input. When we feed back, we have the second sample, which is smaller. The feedback sample is the first one here, so it's bigger. The input signal is smaller there. Then we have a difference between the two. That difference is used to adjust the previous voltage, which was that, so that it corresponds to the new voltage, which is this. And once we do that, we digitize. We get the output, and that output we feed it back through a DSC. So when we feed back, the feedback signal is this one, and the new sample that we take is this one. And the new sample that we take is even lower. So we have the difference between the previous sample and the new sample, which is that. We still have the previous voltage in this unit here. So we use that difference voltage to create the new amplitude that corresponds to this new sample. And so we have the correct amplitude at this point. We digitize it, we go out, and then we get feedback. So any question about how this is happening? So we use, I'll write that, we use new sample plus old sample, but the old sample has been through the digitized process to recreate new sample. So the new sample is what it is, but we create it using the old sample, and we recreate it by getting the difference between the old sample and the new sample, and we recreate the new amplitude there before we digitize. And the reason for doing this is because we know that this stage here introduces quantization noise. And for us to have a chance to reduce quantization noise, we need to put this in a feedback loop, because if we put, remember V out here from an ADC process, we characterize it as V in plus VQ, if you remember the last lecture, that the output is essentially equal to the input signal, but it has an additive noise component that corresponds to VQ. So since we know that feedback can help us reduce VQ, we feed back the signal, but when we feed it back, the inputs, we need to combine it with the input signal, but the input signal is of the new sample. So we create the different signal and we recreate the new signal here. And then we do the digitization process, but we know this digitization process introduces quantization noise. But we know that putting it in a feedback loop like this, we can, by choosing our parameters of this block, the ADC and the DSC, essentially doesn't change the system. This one also doesn't change the signal, other than it adds quantization noise. So the choice of this block is quite crucial. We should choose it so it behaves like a high amplifying, like a unit which amplifies the signal. So that way we can reduce quantization noise. Another question or component. Yeah, so the new samples, we use that to improve the accuracy, and how we do that, we'll see in a moment. The way the new sample is recreated, for those of you who are doing digital communications it's very similar to pulse code modulation. So very similar to that. If you check pulse code modulation or pulse amplitude modulation, the way the ones and zeros are generated will be very similar to what's happening here. So so after the question here is V in. Yeah, but this V in, we create V in, for example, if we are here, we create it from the previous sample, because the previous sample is fed in, and the new sample. So we create that difference. We still have the feedback sample is from the signal which is here. So we have the previous sample, we have the new sample, we create the difference, and we add that up to create our new sample. So our V in, so this V in and V in essentially they're the same, but we are creating V in because we've introduced feedback. We can't feed V in directly there. So we create V in indirectly from the feedback sample and the difference between the previous sample and the new sample, and we recreate it like that. Any other question or comment? So the block diagram with the question mark, we know what it does. Holds previous. We know what it does. It holds the previous sample and then adds to it delta Q, which is difference to current sample. So it holds the previous sample and adds to it delta, which is the difference to current sample, to recreate current sample. So the current sample is created in a roundabout way, but there are major benefits for doing so. So the question is, what's in this block diagram? So it needs to remember the old sample, and it needs to add on the current sample. So actually what's in here is what's in this block diagram is formed by an integrator. An integrator is a summing circuit. We can say it sums cumulatively. So it remembers the previous sum and it adds or subtracts to it, depending on whether delta is plus or minus. If delta is positive, it adds to it. If the new sample is smaller, it subtracts from it. So it's a circuit that can do that is an integrator. So it will add or subtract to the previous sample as desired. And in particular, the type of integrator that is used is a switched capacitor integrator, because this deals with the delta. These are like little DC voltages, and the switched capacitor integrator does that summation quite nicely. So if I draw the block diagram of this, we have V in. Here we have the feedback signal. At this point, we have the integrator. At this point, we can actually use a 1-bit ADC, which is essentially a comparator. And this is V out. We can use this 1-bit DSC, and this one goes back there. And here we have the different signal, and this does the summation. So this is called the delta, comes from there, and the symbol summation comes from the fact that we have integration there, which is the same as summation. The whole of this works at KFS. So the whole of this is oversampled, so works at a much faster rate compared to the Nyquist rate. So we use oversampling for this feedback region. If we draw a model for this, it will look like this. We'll have V in, and we'll have the integrator, and we can draw that with a transfer function, and plus the ADC, because the ADC introduces quantization noise. We can, and this is V out. And because the ADC and DSC, they cancel each other out, this represents just the integrator function. And we can choose V out to be somewhere there. The ADC and DSC, they kind of cancel each other out, but this process introduces an additive noise signal. Out of this, you can write V out in terms of V in. I think we've done probably too much for today. Any other questions? I think we'll finish this on Wednesday. It will take us 10-20 minutes to finish this. The rest of the class on Wednesday will be revision class, and both the classes next week will be revision classes. For Wednesday, many of you, like last Wednesday, had many questions after the lecture, even though it was a revision class. And I probably can explain that by the fact that we are in a very large room. If you're sat at the back, you really can't shout your question. Can I encourage you to, I'll probably put a shared, folder or file, either Word or Excel file somewhere before Wednesday. And if you can type in your question so that you don't have to shout your question from the back of the class. So next Wednesday, we'll spend 20 minutes to finish this sigma to delta ADC stuff. And the rest of the hour will be revision class. Please do either carry your laptop so you can type your question in the shared folder, or I'll share it well in advance, or just type your question in the folder before the class. So then I'll just go through the questions which are in the shared folder. Okay, we'll see you guys on Wednesday. Mohammed, you had a question. Let me just see. If the out is just 0 or 1, it's because the answer to your question, Mohammed, is n is equal to 1. Yeah, but the effective number of bits for this one, effective number of bits for this type of ADC will show that it's equal to n plus 1.5 m, where k is 2 to the power m. So if we oversample if we oversample at high enough rate, we generate the rest of the bits by oversampling. I think that's a question for Marwan rather than Mohammed. So to construct 16 bits, we choose n is equal to 1. We choose m is equal to 10, and we'll have our 16 bits. And that works in real life. So we'll discuss more of this on Wednesday. Okay, see you Wednesday, guys.